Recording is rolling. It is Thursday, August 15th. All right, so you guys remember yesterday took a lot of class to tell you guys about scientific method, measurement. We're looking at measuring equipment, sort of thing. All right, so I do have a triple beam balance. We're going to do a demo. Then we're going to get to scaling algebra trigonometry, which I did yesterday, just ran out of time. But I did give you guys this paper yesterday. On one side are 40 algebra puzzles that I'm not going to grade, but it's extra practice for you guys. You can kind of figure out how much practice you need. But on the opposite side of the same paper are 10 trigonometry puzzles. By the end of class today, I should get you guys started on this, and this is going to be due on Tuesday. And those trigonometry puzzles are really critical to this class. All the trigonometry you're going to see over and over and over for the rest of the class. So that, okay, these students, get them going. Oh, there you go. 10 trig puzzles due on Tuesday. Okay. All right, so you guys feel with the agenda, what we're doing? All right. So let's look at, let's review something from yesterday. I told you guys about mass versus weight. Really want to see if you guys remember this. Okay. You guys remember 1 kilogram? This is 1 kilogram. This is your largest lab weight. You guys are going to get these boxes of lab weights, right? Different values. So here's the big one, 1 kilogram. Suppose I push it back and forth like this. Ooh, does it take some effort to change its state of motion? Definitely it does. All right. What if I was up on the moon and I did this exactly on the moon? Would it feel the same on the moon? Yeah. Guys, is 1 kilogram of material, 1 kilogram of inertia, also 1 kilogram of inertia on the moon? Yeah, 1 kilogram is 1 kilogram everywhere, right? It's the same mass everywhere, right? If you're throwing this back and forth on the space station, you and your friends, right? You're going to feel it clunk, right? You definitely feel different than this hitting you, clunk, right? Even though these are completely different weights. And there's no weight in space if you're in deep space just floating around. But if somebody throws it at you, that takes more stopping force for this one, right? Feel that, right? Notice I'm pushing this back and forth horizontally, which has nothing to do with how the Earth is pulling on it vertically. Right? Now that's weight. And if you pick it up, right. Now you're getting a sense of its weight because that takes a force, and that's a different concept than mass. Right? Because remember, mass is going to be measured in kilograms. Force or weight is going to be measured in newtons. Those are totally different units, right? What if I pick this up on the moon? Is it easier to pick this up on the moon? Definitely, because this has a lot less weight on the moon, a lot less gravity force on the moon. Right. And how are you going to measure mass? All right. Well, one way you can use this triple beam balance I was telling you guys about. I'm saying this one works on the seesaw method. Right. Now, I do have 2 cameras I'm presenting to. We got the in-class projector, and we got the anybody watching the video at home. I got a video camera over here. Right. So it's a really tight space, but I'll do the best I can here. Right. So let's take a look. I got a plate here where I can set weights on. So of course I'll have this vertical, but I'll set some weights on it. Okay? And then I got these sliders, right? The sliders. So this one's 100 grams at a time. There's one in the back, it's 10 grams at a time. Okay? And there's one in the front that's just 1 gram slider at a time, 1 gram at a time. Okay? And when I level it out, what'll happen is this right here. So when I first set the weight on, it goes clunk like that, and it misaligns. See that little white line? If it aligns with that needle. So when I slide these things around, when I slide this around, right, this will eventually, it'll hit that 0. And when it hits that 0, it's balanced. And then I know how to correct weight reading. So quick demo here. If you've been to the doctor's office, they probably put you on a scale. It's the same principle as this one. I'm going to use the 200 grams here. Here's 200 grams, fed on 200 grams. Right, now the thing just misaligned. I can take the big one and go plunk, plunk, lock them into 200. Right, and that, right, sort of take my word for it. Maybe you can kind of see it in class. It just levels this out. Just leveled at 200 grams exactly. Okay. Or what if I set the big one plunk at 100 grams and I move to a little, I should say the medium slider to 100 also. So 100 plus 100 makes 200. And now it's rebalancing at the 0 mark. Okay. So there's 2 different ways I know this is 200 grams. Okay. So one more question about the scale. Let's see if you guys remember this from yesterday. If I take the scale to the moon, and I put this 200 grams mass on this scale on the moon, will the scale also tell me that it weighs 200 grams or has mass 200 grams? How many guys say yes? Yes, it does. Yeah. All right, you guys remember that. So, because the seesaw principle, it doesn't matter the strength of gravity. All right, so you guys good with that? All right, so let's switch over to, I'm going to pick up from yesterday that PowerPoint. So let's see, switch my screen over here. All right, actually, let me rewind a little bit to some last stuff you guys saw yesterday. You guys remember we were doing dimensional analysis? You guys remember that? All right, you guys saw this one. We got this solar question, which is a really good challenge problem. if you guys like, I kind of recommend maybe you take out a blank piece of paper over the weekend, see if you guys can solve this one from scratch. If you can, it's a really good skill to have. Okay. All right, anyway, we're gonna plug along here. All right, scaling, new concept. All right, so what if you scale something up in size? Different physical properties will change at different rates. I want you guys to see this with this cube. And then when you guys see other types of shapes, the exact same scaling principles apply. Right, tell you guys some examples going on. You guys see a little tiny box down here? A little tiny box? It's like 1 by 1 by 1. You guys see that? Right? You guys see a big old crate that's like 3 by 3 by 3? Right? You guys see that? Right? So what if I blow this up? Maybe kind of like a balloon. Like the whole little tiny cube is expanding into the big crate, right? So anything that's linear factor is going to be linear factor 3. So the big crate is 3 times as wide, 3 times the depth, and 3 times the height of the little tiny box. Guess that, right? Anything that's linear is also a factor 3. So if you like walk around the little box and then you walk around the big crate, that's also 3 times the walking distance. That's the perimeter. Okay. But what about some other physical properties? Like what if you paint the little tiny box and then you paint the big crate? How many times the paint do you need? And it's not 3. How many times paint? What do you think? Ooh, not quite. A little bit less, a little bit less. All right, so I'm just painting the surface. Let's just focus on one surface. Let's say the front surface. You guys see this 1 by 1 square right here? Let's just say I paint that, right? And then the big crate, I'll do, well, the equivalent. So is that 3 by 3, right? Guys, 3 by 3 is what? 9. Is that 9 times the paint just for that one surface, right? Now, if I do all the other surfaces, that's also a factor of 9, right? Right. Okay. Right. So the principle is this: it's a linear expansion of 3, right? But painting a surface, that's a 2-dimensional concept, right? So that's like squared. So 3 squared is 9, right? You guys got that? So okay, so it's the surface area, the paint coat. Ooh, shadow. Ooh, what if that little box casts a shadow and the big crate casts a shadow? Think the shadow's 9 times as big? Yep. Right. How about what if it's not a crate? What about how about this? What if there's 2 planets? I got a little tiny planet and I got a big planet. Let's say the ratio of the diameter is 3 to 1, right? So 3 times the diameter, right? Now different properties of those planets are going to change at different rates, right? How many times the surface area does the big planet have compared to the little planet? It's 3 times the diameter has how many times the surface area? Sir, 9. Yeah, it's like 9 times the land you could walk around on. Yeah, sure would be. Yeah, right. And one more property let's look at is a 3-dimensional property like volume. Let's see, mass could occupy volume. I guess weight could occupy volume. Right. So, how many times the volume is that big crate compared to that little tiny box? How many times the volume? Who said 27? 27, right? Because here, if you count it, do you guys see there's like 3 stories? I got a first story, a second story, and a third story. You see that, right? Now, in the first story, I can fit 9 little boxes, 3 by 3. There's 9 boxes down there in the first story, right? And then 9 on top of that, 9 on top of that. So that's 27, right? Right. And then the scaling principle goes like this. If it was a linear expansion of 3, and this is a 3-dimensional concept, right? Volume, right? Mass occupies volume, right? That's power of 3, and 3 to 3 is 27. Okay. Right, let's go back to our 2 planets. You guys remember the little planet and the big planet has 3 times the diameter, right? How much more massive is that big planet compared to the little planet? 27? 27 times the mass, right? Now, when you have these different factors going around, another question you might possibly eventually see in this class is how do the gravity fields compare at the surface, right? Now, if you want to figure out gravity field, you have to know the radial size, okay, which is 3 times. You also have to know something about the mass, which is 27 times. You guys see that we'd be considering these different physical properties that scaled up at different rates? Right, and that'll eventually lead to being able to answer that question. So I wonder what the gravity field is at the surface. Right, you guys got that? Right. How about this? I think you guys are going to see a question. Eventually, it has to do with like an elephant grows up. So what if you have a little baby elephant? And he grows up to a big adult elephant. He's like 3 times the height, right? 3 times as tall, right? But he didn't just get taller. He also got wider and longer. Right? Guys, a 3 times as tall elephant weighs how much compared to little elephant? 27 times. 27 times the weight. Right. And how many times the surface area of his ears? 9. Right. right? Because it's right here. It's all the same. It doesn't have to be a cube, right? You can make it any shape as long as it scales up. Okay. Could be a planet. Could be an elephant. All right. Square cube law. This is effectively the same thing. It's just a specific application of this. So especially if you have an airship or maybe a cargo ship. Right? There's a lot of cargo trades across the Pacific Ocean. Right? Like, what's the most efficient way to ship cargo? Right. Well, what people realize here, I'll zip through this one a little bit fast. Suppose you have a little tiny cargo ship. You make a big cargo ship that's 3 times the diameter, but also 3 times as long and 3 times as high. Right. Right. All the scaling principles also apply to, well, I guess both these ships. Right. So we're going to scale it by a linear factor of 3. Right. That means that it's going to have, guys, how much times the area plowing through the water for the cargo ship? How many times the area? Well, hold on. Area is 9 times the area, right? Do you guys think that drag force is probably proportional to that area that it's plowing through? Yeah. So it turns out, learned this in a few weeks, right? Turns out to be 9 times the drag force. Okay. So now we have to burn more fuel. So is that a bad idea? But hold on a minute. The big container ship can hold, guess how many times the volume compared to the little one? 27. 27 times the carrying capacity. So even though it's more drag force, it's also like a bunch more cargo it can carry. Right? So what people figure out over the years is you just make these container ships as big as you can possibly make them, which, the limiting factors is like how big a port space do we have, or how big is the Panama Canal? So that's kind of what limits it at this point. Right? All right. So that's just scaling all over again. All right. You guys get a fractions table. You're like, hey, what is 3 over 7? Okay, hey, it looks like that. There you go. There's 3 over 7. All right. All right. So you guys got some paper out. Oh yeah, I see you guys got paper out. If you sort on paper, I got some paper on these 2 stools right here. Go ahead and solve that algebra equation right there. Give you guys a little time. Solve that algebra equation. If you know what you're doing, go ahead. If you're totally stuck, you're like, oh, I haven't seen this in like a year and 3 months. All right. So the process for algebra, if you want to solve for x, so your goal is to solve for that x I put in the green box, is you want to undo everything that's already there. And I put all the PEMDAS here. I see parentheses, I see exponent, I see multiplication, division, I see addition, subtraction. Like, they're all packed into this one example. You have to undo that everything's there. Now, as long as you do to one side of the equation, same thing you do to the other side of the equation, then everything's still balanced. You're still getting a true statement. Okay? Now, you can go through a series of steps, and the very last step should just have x isolated and say x equals something. So give you guys some time. You got some time. Okay. When you get the answer, raise your hand. Who's going to get this? Right. See how much you got.
X equals 9 bits.
A little bit different. Okay, and you're at 7. 7. You guys get 7. Okay. 7 is correct. But there's also another correct answer. Does anybody know the other correct answer? 7 and also what? Which guy?
14 thirds.
Not quite. All right, that's right. All right. So let's try it out. All right. So you guys tell me, what's the very first step you guys did? Square root. Yeah, because you have to. Okay, there is something being squared. I have to undo that so I can like unbury this x. So I'm going to square root both sides. Guys, what is the square root of 4? 2 and also -2. The problem splits right away. Right, that's going to lead to 2 separate answers. You guys see that? 2 also -2. Okay. All right. So we're done with the square. The square is gone. Right. I know that inside expression could be 2 or -2 would also work. Okay. Right. Guys, what's the next step? Multiply by 5. Right. I see a big old fraction. Right. Let's get rid of the 5 times 5. 2 times 5, so like 10. Right. And then the negative version over there. Okay. All right. So -10 over 10. Right. So that numerator. Is that all right? All right. What's the next step? Add 11. Guys, what's 10 plus 11? 21. What is -10 plus 11? 1, right? 1, right. If you're in debt $10, then you get $11. Now you're okay. All right. So like that. Is that right? And one step away. What's the very last step? Yep. Divide by that coefficient 3. 1 over 3 is 7, and then 1 over 3 is 1 over 3. So third. Okay. Now, if you ever go through this algebra process and you get to the end, like, I don't know, is that right? What if I made a mistake? And take your final answer, go back, plug it into the original expression, and it should give you a true statement. All right, so let's see if it does. Let's start with the 7. Nice integer there. Guys, what's 3 times 7? 21 minus 11 is 10. Divided by 5 is 2. Squared is 4. Oh, bing! It works. Right. Do you guys think the 1/3 is really going to work? Let's see if it does. What is 3 times a third? Huh? Yeah, 1, right? Okay, 1. Right. Minus 11 is -10. Divided by 5 is -2. Squared is also 4. Hey, that works too. Yeah. So both those work. Okay. All right. Guys good? So this one. That last one we just did is on your thumbnails. This is a little bit bonus. So if you want access to this one, you put your notes right now. You can download this book if you haven't already. All right. So same thing as before. Solve for x. Right. While you guys are solving this one, let's talk about algebra a little bit. Kind of where does this come from? This whole process. That word algebra, or really anything that starts with AL, comes from what language? What language has all the owl this and owl that? Algebra. Latin. A little bit east. Keep going east. Huh? Arabic. Yeah, Arabic. Right. So Middle East, Arabic. That's where the process algebra comes from. So, like, why do you usually solve for x? Why am I having you solve for x? So the history goes, in Arabic, algebra stands for the system of solving for unknown parts, something like that. And there was an Arabic character they solved for called al-Shay'an, like the unknown thing. Right? Well, okay, so think about al-Shay'an, chef. The Greek, I think in Greek there's no sh sound, chef. Right? So they went with the Greek letter chi. It looks like a curly x, and then by the time it got over to Latin, it became a x. Right? So that's why you solve for x. Okay. All right. So what are you guys getting? Who knows? What's the answer? Yep.
For -7.
All right, and you got same thing? Yeah, okay. So it's multiple, guys, so tell me 4 and also -2/7. I think that's right. Let's see. What'd you guys do first? Square root. So that's plus or minus 3. I mean, same format as the last one, right? It's got all the PIMDOS in it. Right? Do what both sides? Times 5. Right? So, okay, that brings us up here. Right? That okay? Right. Okay, so square root of both sides, that split it to plus or minus. Then times 5. 3 times 5 is 15. Right? Next step. Add 13. Because what is 15 plus 13? 28. What is -15 plus 13? -2. Yeah. Okay. It's like that. And last step is divide by 7. There you go. Bam. And that's exactly what you guys told me it was. Okay. So yeah. So if you got those, then you're probably pretty good to go on algebra. If you really struggled with that, then again, I highly recommend you solve a bunch of those 40 algebra puzzles that I gave you guys. Okay. All right. Any questions more on algebra? All right. Let's see what I got next here. Is graphs. Right, so there's a number of graphs you guys are going to see. This is a really common one. I might just rattle this phrase off. Y equals mx plus b. Guys, every time in class I say y equals mx plus b, you guys are thinking what graph shape? Linear. Yeah, exactly. So that could be like this, right? So in this case, m stands for slope. M is used for a lot of things. I remember as a variable, it was mass. As a unit, it was meters. As a prefix, it was milli. And now it could even represent slope. Right? Except you'll probably see numbers. So it might say like, y equals 3x plus 1. And then be able to create this really fast. In your mind, you should like jump straight to this. Okay, y equals 3x plus 1. I now have a rise over run of up 3 over 1. That's the slope, right? And then the whole thing shifts up 1 unit, and then your y-intercept is 1. Y equals 3x plus 1. This is 3 over 1. This is 1. Okay, right, guys do it. Right. How about any other kind of graphs? So of course, there's a bunch of type graph shapes floating around in the world. You guys are going to do a bunch of labs in this class, but there's really only a small handful of graph shapes you're really ever going to see in this class. And I try to put them all on this one side right here. Right? So first one, what if it turns out that there's no relationship between two variables? And that'll be true for a lot of cases. So say like, hey, what if I make this weight like 3 times as heavy, right? 3 times the weight, right? I wonder how does that affect, some other variable, like how much time it takes or something, right? And then what if I do like 6 times the weight, 9 times the weight? And so you get your points, you make X bigger, 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 bigger. And then the other variable doesn't really respond. It's like it doesn't really care, right? I could say that there's no relationship between those two variables, right? And that might be a horizontal graph like that. You could also have the vertical version where you keep changing Y and X doesn't respond, right? Like you change one variable and the other doesn't care what the other ones do. There's just no relationship between the two, right? You guys see the reasoning behind that, right? Okay. Right, next one. Linear or direct. Linear usually goes through the origin, or sorry, I meant to say direct. Direct usually goes through the origin. It's a type of linear. So a lot of times they'll look like that. Okay. If you triple X, then Y also gets tripled. Now X and Y could be stand-ins for any number of physical variables in this class. You got like mass and distance and time and speed and force. So you got so many variables, right? Right. Inverse relationship. Ooh. For example, Y equals 1 over X. What do you guys think that one's going to look like? Inverse. How about this? What do you guys think about that? I'll give you guys a story. What if you have a wagon, right, and the wagon is empty, and you pull on it with a force? Yeah, it's going to accelerate, right? It's really going to move. What if you take a big old weight, big old boulder? You put a big old boulder in your wagon, right? Now it's super massive, right? Then you pull your wagon with the same force as before. Is it going to move as much? No, right? So the more mass, the less it's going to move, the less it's going to accelerate. Do you think that's one of these right here, this inverse relationship? As I increase the mass, the acceleration decreases, right? How many guys were thinking something about like that right there, right? Guys think? It's an inverse, that's called Newton's second law of motion. I just walked you guys through, okay? Inverse relationship, right? Notice I'm not connecting dot to dot. You guys see that? I'm doing a line of best fit, right? Because when you guys get measurements, a lot of times there's some error either in like the equipment itself or how you measured it. Right? So this is a little plus or minus. Sorry. Right. Parabolas and roots like Y equals X squared or Y equals the square root of X. These are really common. Now, before I draw the curve of best fit through it, at a glance, a lot of times these start out looking linear, but if you kind of reason through it, you can sort of figure out why that might not be the case. Right. So there's a parabola, here's a square root, right? Which is actually the same shape. Actually, those two graphs are just flipped. If you flip what is X and what is Y, then one becomes the other. So those are kind of the same graph. Okay. Right. So sideways parabola is the root. Okay. And that should take us all the way to December. Pretty sure you're not going to see any other graph other than just those 5 from here to December. Unless I'm forgetting something. Okay. Sinusoidal. So about January time frame, we're going to break out some pendulums. We're going to put some masses on some springs. Like, wow, 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 wow. It's going to oscillate. You guys know what Y equals sin X looks like? Right, maybe it looks about like that. It's bow, wow, wow, oscillates back and forth. Okay. I think I'll cover the bases right there. Okay. So you guys good on graphs? All right. That's one of your thumbnails. Good to go. All right. All right. Ooh, quadratic formula. Right. So this pertains to parabolas. Right. That was one of the graphs we're looking at, parabola. Right. Say you shift it around, maybe a little bit more fancy. See an upside down parabola right there is my example. If you can get it in that standard form, at squared plus bt plus c equals 0, where maybe t is the variable in this case, right? If you have the quadratic formula memorized, you can just get the answer really fast, right? And usually there's like 2 solutions. Give you guys a physics example. So there's a question in one of these textbooks back there, like you're standing on the ground, there's a 4-story building next to you. You see your friend way up in the 4th floor. Your friend says, "Hey, you down there? Pass me those keys. Throw me the keys." Right, so you got some keys. You're like, ugh, you chuck them straight up. And the question is, when does your friend up in the 4th floor catch the keys? If you think about it, could he catch them on the way up? Or what if he misses them? Wow, and then you overshoots and then he catches them on the way down. But there'd be actually 2 different times he possibly catches those keys. There could be 2 possible answers, right? Right. So you release the keys, you can catch them on the way up or on the way down, right? That could be answered by this right here, right? So height of those keys as a function of time turns out to be parabolic, just like that. Right. And then show of hands, does anybody have that memorized? Quadratic formula memorized? Yeah, some of you guys do. Yeah, so you don't necessarily have to memorize it for this class, but you could kind of recommend it. That could be good to know. Okay. All right, circles and spheres. Some geometry here. All right, so let's start with circles. Circumference of a circle and area of a circle. I see students mix these up all the time. Which one's which? Does anybody feel pretty good about what is the circumference of a circle? Who knows that? What do you think? Times pi, diameter times pi, I think, right? Pi times diameter. Yeah, that'll do it. Pi times diameter, right? What about in terms of radius? What you got? Yeah. The perimeter of a circle, right? Right. So here's what I'm looking for. I'm looking for circumference equals 2 pi r. That's what I'm looking for. Yeah. And since 2 times the radius is the diameter, then it'll also be diameter times pi. That works too. Okay. So 2 pi r. Now, what a lot of students mix that up with is this next one. Area of a circle is pi r squared. I guess that. So okay, so you got a circle. I give you the radius. It asks you what's the circumference, the perimeter around, and what's the area, right? How much area does it cover? If you want to paint it, right? All right, so let me show you guys a trick here that's actually going to be useful for probably every single formula that you guys see in this class. So this is a really general trick right here. Right? Let's ignore the pi or the 2 pi. Ignore that. And let's just look at this as a proportionality. Say you're comparing a small circle to a big circle. Okay. Right? So like 3 times the radius. Right? Right. Do you guys see that circumference then would be very simply proportional to the radius? Right. Now think in terms of units. Guys, radius. Could you measure radius in meters? That could work, right? Or inches or feet, right? But you wouldn't measure radius in like square feet. That wouldn't make any sense, right? So you can measure it in feet, right? Right. In this class, meters, right? And circumference. If you want to walk all the way around the circle, that could also be in like meters or feet or inches too, couldn't it? Right. So they would be the same unit, right? So if radius is in meters, circumference could also be in meters, right? That's true, right? Versus, let's do the contrasting. What about the area? Okay, so radius again could be in meters. But guys, if you square that, what unit does that give you? Meter squared, like square meters, right? Right? Or if you like square feet, because then you can just look at the floor and count tiles. Every single tile is a square foot, isn't it? Right? Hey, that describes an area. So now area is proportional to like square meters, which definitely makes sense. They could describe an area. Is it? Okay, so if you follow what I just said, then you'll never have to mix up these two formulas again. Right? Okay, circumference proportional radius, area proportional radius squared. Okay. Right. How about spheres? Here's a little trickier. Does anybody know what is the surface area of a sphere? Okay, here, give it to you. Ends up being 4 pi r squared. But again, notice area is proportional to radius squared because it has to be. Because see, if I had radius in meters and square that gets you square meters, there's an area already times 4 pi. You get the answer. Okay. All right. Last one, volume of a sphere. What do you think volume is proportional to? R to the power of what? 3. Exactly. Has to be something to do with r cubed, right? If I have r times r times r, now I have a little box. That's a volume, right? Now, what do I multiply that little box by to get to turn it from a box into a sphere? Does anybody know? Yeah. 4/3 pi. 4/3 pi. There you go. Got it. All right. So you guys get there? I really wish I'd put this one on your thumbnail notes. So oops, I missed that on your thumbnail notes, but I think it's pretty good to know those, especially the circles. Okay. So you guys got those? Okay. All right. Yeah, I do want to do a lab with you guys. We'll see what we can fit in. Right. Let's go to triangles. Triangle time. Do you guys know what is Pythagorean theorem? Boom, winner. A squared plus b squared is c squared. Okay, so that pink square plus that green square is always going to equal that yellow square, as long as you have a right triangle. That only works on right triangles, right? Okay, which if you have any other type of triangle, you can always split it up into smaller triangles that are right triangles, so you can always make use of this. Right? If it's not a right triangle, I think it's something called like law of cosines. It's kind of a generalized version of that, but I don't even have a poster for that. Right, guys, what is the area of that blue triangle? Area. You want to paint it. How about this? What if it was a rectangle and it was like A wide and B tall? You guys see like a rectangle here? Could the area of this rectangle be just base times height, A times B, right? Now this triangle, if you slice that rectangle in half, corner to corner, that's the triangle, isn't it? Oh, half. So is that 1/2 base height, right? Base height over there. Okay. Now I say a right triangle. Right triangle is really convenient because the legs are the base and the height, right? Now, really, 1/2 base height works for any triangle, but if it's not a right triangle, it's a little bit tricky because you have to figure out what's the altitude of the triangle, so it's a little bit extra step, right? But if it's a right triangle, it's just the legs multiplied divided by 2. Okay? All right. This one here. Okay, guys, this slide right here is one of the most critically important slides you guys are going to see in this class. This is never going to go away. You're going to see this over and over. That whole trig page I gave you with those 10 trig puzzles, you can solve all of those pretty much with this right here. Okay, so sine, cosine, tangent. We're looking at trig ratios. So I got a nice right triangle up here, up to the right. Guess that triangle. It is a right triangle, right? Except if you look really close, it have some physics additions to it. So really what this is some black vector. You guys see an arrow? It looks like an arrow with an arrowhead on it, right? That black vector, something going up to the right, right? And it's split into these dashed components. So I'm dashing off these components, right? Now this could represent a bunch of different things. For example, what if I'm pushing something up to the right, or like kicking a soccer ball up to the right? And the question would be, well, how much up and how much to the right? I'd have to quantify that, right? Or what if you're walking northeast, and I would say, how much north and how much east, right? Or like, what if you fire a cannonball, right? Let me switch over here so I can actually kind of draw this out for you guys. Right. Like, what if I have this mass sitting in the middle of the floor, right? And I push up to the right with some force. Now it's moving, right? And I want to know, like, how much am I pushing it? Right. So I'm pushing with some force, right, in that direction, right? And I'm sitting it up and to the right. But the next question is going to be, well, how much up and how much to the right? So I need to break that into components. And that's where this right triangle geometry is always going to pop out, right? Right. How much up? How much to the right? Right. Well, it depends how much I was pushing altogether. Let's say I was pushing like 10 newtons of force, for example, right? It also depends on the angle I was pushing at. I'm going to make up an angle. I'm going to call this, let's call it 37 degrees. Right. There's a reason I picked that number. Okay. Right. You guys get that? Right. So let's flip back over to this PowerPoint and see how are we going to figure out how much up and how much to the right, so that you can solve a bunch of physics problems in here. Right. Now, in math, I bet you guys learned sort of these definitions of what is sine, cosine, and tangent of this blue angle theta. These are all relative to that blue angle theta. Okay. Right. Do you guys hear something called a SOHCAHTOA? Right. SOHCAHTOA. Right. So it's a mnemonic device. SOH. Sine is equal to opposite over hypotenuse. CAH. Cosine is adjacent over hypotenuse. TOA. Tangent is opposite over adjacent. Right. Here I just did A, B, and C, but it's the same idea. Right. Right. So notice these two legs. The leg B is not touching the angle theta. That makes it opposite. The leg A is adjacent to the angle theta. It's touching it. So it's adjacent. Right? And of course, the hypotenuse is longest side opposite of the right angle. Okay. Right. Okay, so we've got that. Now, take these definitions as they are. So sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. Right. And we're going to rearrange this a little bit to get how you normally need it in this class, because there's a specific application of this that you need like 90% of the time in this class, right? It goes like this. Right? Notice on the paper I just wrote, right? I gave you guys what is C. I said I'm pushing with like 10 newtons of force, and I gave you this angle like 37 degrees, right? That's just what I gave you, right? And I want to know what is B and what is A. So I want to know this opposite side and this adjacent side. Hey, can I do a little algebra switcheroo? Like we were just doing some algebra a few minutes ago. Hey, can I solve for B and solve for A? Right? Who can tell me from this top box? You see a little arrow? You gotta put it right here, right here. What's going to go in this box? B equals what? Who knows what goes in this box? B equals. It's the same process we just did a few minutes back. Can you cross multiply the C? Can you do that? Cross multiply the C? That's it. That's it. Right. So again, like 90% of the time in this class, you're going to know effectively the hypotenuse of the triangle. So it'll be the original vector, right? And you'd probably also be given this angle. And so if you do C times sine theta, that gives you this opposite side, right? What do you guys think is going to go in this pink box right here? A is equal to what? C cosine theta. Yeah, just like that. C times cosine theta. Right. Right, guys, those two boxes that I just popped in right there, right? Know those two like the back of your hand, because you're going to apply that like hundreds of times in this class. Okay. I'll give you some original vector. I'll give you an angle. Say see sine theta, see cosine theta. Boom! I got the two legs done. All right, you guys see that? Let's do an example. Let's bring us new. Stop share. Come on, stop share. No. Okay, here we go. Oh, look at this. I gave you the hypotenuse of a right triangle, and I gave you the angle that's at. Right? So see if you guys follow what we just did. This side is equal to what times what? 10 newtons times what if 37 degrees, sine or cosine? Sine. Yeah, sine of 37 degrees. Okay. Let's see what that is. Oh, okay. Let's do, and make sure your calculator is programmed in degrees and not radians in case that's an issue. Okay, so 10 times sine of 37 degrees. Okay, see what we get. Right, that is, 6.0 something something. Is it okay if I round that to about 6? It's like 6.0. Okay, I'm gonna call it 6.0. 6.0. And in physics, these numbers have units attached. I'm gonna say newtons. Right, so it's like a like a pushing force. Right. So when I was pushing it 10 total newtons at a 37-degree angle, like how much up? Oh, 6 newtons. Right. Well, the other question is how much to the right? See if you guys follow that. Guys, this component right here is equal to what times what? 10 newtons times cosine of 37 degrees. Because this leg is touching the angle, so it's adjacent to it. So cosine, right? I'm translating from hypotenuse to adjacent leg. Okay? Let's do that. Now, this calculator, what's one thing really nice, I can just use these arrow keys. I can scroll up, scroll over, and where the sine used to be, I can pop in a cosine, because everything else is the same. Okay? Say what I get. 7.99. Is it okay if I just call that about 8? Is that okay? About 8? I'm gonna call it 8. 8. And that would be newtons, wouldn't it? Right, so got it. Right, so 10 newtons at a 37-degree angle, that's 6 newtons up and 8 newtons across altogether, right? So if you just, right? Or what if it wasn't newtons? What if you kicked a soccer ball and pow, you kick it at a 37-degree angle from the horizontal, right? Well, now it's going across the field at like 8 meters per second. Right, guys, in fact, if you stand back and look at it, guys, look at these values, right, for sides of a triangle, 6, 8, 10. Guys, that is if you reduce that ratio, that is a what to what to what ratio? Divide everything by 2. 3, 4, 5. Is that a 3, 4, 5 right triangle right there? Hey, do you guys think that all 3, 4, 5 right triangles have a 37-degree angle in them? Yep, they sure do. Right. Speaking of that angle, that's the last part of this slide I have to hit. So let's go back over. Look at this. Whoop, and switch over. Look at the slide. Right. So, okay. Questions so far? What's going on? All right, guys. All right. This very last box I haven't filled in yet. I want to do something a little bit different with it. I want to show you guys how to extract an angle if you know everything about the sides of a right triangle. Right? Because once you know enough information about a triangle, like everything else becomes locked in place. Right? What if you're loaded up on side information? Like, what are these angles? Right? Well, I know a 3, 4, 5 right triangle better have a 37-degree angle in it probably. Right? But how could I get it for any other kind of triangle? Right? So let's you could cross multiply the a and say b is a tan theta. That would be true too. But I want to do something a little different. Right? I want to extract this angle theta. Right? Does anybody know how to do this? How to get an angle out of a trig function? Right? You have to like undo the trig function, and you do that by an inverse trig. You guys ever heard like a inverse sine, inverse cosine, inverse tan? Maybe. Right? We're about to do that. Right? Or sometimes they call it like arctan. Right? So we're gonna do this. Right, I'm going to say theta equals, and I have to apply an inverse tan of this fraction, that ratio b over a. You could also do it with sine and cosine. So theta could also be inverse sine of b over c or inverse cosine of a over c. I'm just going to play off tangent for this one. Okay, see that? Right, so here's the takeaway. If you have a trig function of an angle, sine of theta, cosine theta, tan theta, that will always spit you out a ratio. If you have an inverse trig of a ratio, that will always spit you out an angle. Okay? So let me show you on the calculator that this does work. Because we definitely got overkill information on this triangle. Let's say I just had the sides. It was like 6, 8, and 10, or 3, 4, and 5. Suppose I didn't know what this angle was. is the calculator going to tell me it's second? Right, let's see. So should I do theta equals? Because here's my theta, right? I'm gonna play off tangent. So I'm gonna do inverse tan. Notice I'm not taking the tangent, I'm taking inverse tan, also called arctan. If you're playing on Microsoft Excel, they're looking for inverse tan. But inverse trigs, I'm doing of a ratio. Now, tangent, inverse tan has something to do with the two legs of the triangle, right? See if you guys are following. Because what number goes in the numerator and what goes in the denominator? It's what over what? Yeah, b over a. In this case, 6 over 8. Right? Is that true? 6 over 8? Right. And since it's physics, I'm going to write it in newtons and newtons, although that immediately goes away anyway. Okay. All right. Straight up. Oh, how do you access that on the calculator? Do you guys see this button says second? If you have this model calculator, or class set, second, and then hit tangent. And look, it doesn't say tangent, it says inverse tan. You see that? Inverse tan? Right? I'm going to type 6 over 8, right? Like opposite over adjacent. Right? Now, before I hit enter, right, I think if you guys are following, you know exactly what the calculator screen is about to tell me. What number is about to pop up on my screen? 37, right, to represent 37 degrees. Ah, you guys are on. Right, okay, so it's like 36.869. Okay, so 36.9. Sometimes I write 36.9 degrees. Okay, you guys get there? Okay. Yeah, so every 3, 4, 5 right triangle will have that 36.9 degree angle in it. Okay, you guys right? All right. All right, let's see. I think we're pretty close to the end of this presentation today. Let me double check. Sure I'm not forgetting anything. Okay, a lab. I'll have you guys break out the protractors and rulers pretty soon. Okay, then linear motion we'll save for another time. All right, so let me help you guys out as much as I can on this type paper. You guys remember this one? And so I got algebra puzzles on one side. This is a little extra. I think we'll have some time tomorrow. You guys can do some extra practice, ask me any questions. Okay, but this side right here, this is the side I'm gonna pick up on Tuesday and grade. Let's how about number? Let's do number one. Number one. You guys see number one? Let's see that one. Okay. So, oh, I should say too, everybody has different numbers. So I have like 10 different versions of a bunch of different papers. All right, but all right, let's try this out. Okay, so I'm gonna play off this triangle. Okay. I got 30. Right, so I got some vector. It could be one of many types of vector. It could be speed, velocity vector. It could be a force vector. I'm going to split this into components. Say like how much over, how much up. Okay, so we got to split that into components. Okay, so everybody has right. Every single one of these questions pertains to a right triangle geometry, just like that. Okay. Okay. Now my paper says this alpha right here is 30 degrees. So I'm going to write in 30 degrees. Although your paper is probably a different number, that's okay. Right? And I also have a hypotenuse z of 50 meters. Okay, so this is meters. Maybe we're walking around on a field. What if I walk 50 meters at a 30-degree angle, say like north of east or something, right? How far east have I walked and how far north have I walked in terms of coordinates, right? Right, we're about to answer that. Right? Well, in time, because maybe I want this other angle also. Guys, if alpha is 30 degrees, what is beta? I haven't actually told you guys this yet, but I bet you guys know. Guys, what is beta? Huh? Okay. Oh, yeah, that's the rule. Alpha and beta have to always add up to 90 degrees. You guys see that? Yeah, so this must be 60 degrees. Okay. Here, maybe write that down in your notes if you don't have that yet. Alpha plus beta must always be 90 degrees. Okay. No, that's true for all flat triangles. And when I give you guys the protractors, eventually probably next week, I think, you guys can see that for yourself. You can measure it and see that's always true. Okay. Oh, right, how about x? So this side x adjacent to 30 degrees, that could be what times what? 50 meters times what? Sine or cosine of 30 degrees? Cosine of 30 degrees. Okay. You could also do sine of 60 degrees. That would give you the same answer. Okay. And we do 50 cosine 30 degrees. That's telling me 43.3 meters. Okay, so in terms of walking across the field, looks like it went 43.3 meters east. Right? Okay, got that? Right, and how far north? Y equals, okay, so I'm gonna start off with 50 meters total, or like that diagonal, times what? About sine of 30 degrees. Okay, I can do that. Let's see what that 50 sine 30 degrees. Ooh, exactly 25. In this case, meters. Hey, good rule of thumb. Guys, sine of 30 degrees is always 1/2 exactly. And you see that here. Right? So 25 meters. Okay, just like that. All right, you guys all right? Let me show you guys if I do this the other way. This is also 50 meters times cosine of 60 degrees. Let's see if it is. Cosine 60 degrees. Hey, it's the same thing, same thing. Okay, guys good? All right, I'll have to be our pause point today. Yeah, we should have some time in class tomorrow.